SPC7 is going to slow down the pace a little bit. In the last lesson, SPC6, we had a look at the profound photoelectric effect, which probably took a few of you a little while to get your head around. In this lesson, all we're going to discuss is one unit. So units are the things we use to quantify what we're talking about. So we measure our speed in meters per second, we measure our time in seconds, our energy in joules, etc. These are the things that you keep on forgetting to put at the end of your numbers on your test papers, costing you points. But today we're just going to discuss one of these units, one you haven't come across before. We want to introduce you to it. It's this little one here. It's denoted by a lowercase e followed by an uppercase V. It's not strictly an SI unit actually, but it's used quite commonly by the likes of particle physicists. We'll see why. It's called the electron volt, so the lowercase e stands for electron and the uppercase V stands for volt. We'll see where this name comes from in a minute. So let's have a look at our little sketching pad. So if we've got a pair of plates, go away. Here we go. Right, one of them is positively charged and one of them is negatively charged. And we can say that there's actually some voltage across them. But let's leave the number off for the minute. And if we stick an electron in here, which has a negative charge, it is of course going to be repelled away from the minus end and towards the positive end of these two plates. And the higher the voltage between these, the stronger this repulsion and the greater this attraction here. So as we increase the voltage across these plates, the electron is going to whiz across faster and faster and faster and faster. And we define the electron to be the amount of energy which the electron gains if it passes between two plates with 1 volt of potential difference between them. And it turns out that's reasonably easy to quantify. So the charge on one electron, so remember it's measured in coulombs, the charge on an electron is actually very small. It's 1.6 times 10 to the minus 19 coulombs. So a very, very small charge. We get a lot of them for a coulomb's worth of charge. And if we have a look at the equation which relates voltage, energy and charge, we know that voltage is work done per unit of charge. So this would be volts, this would be in joules, and this would be in coulombs. So we can see if we're saying that 1 electron volt is the amount of energy that 1 electron gains from passing across a potential difference of 1 volt, then we can stick in 1 volt here, we can stick on 1 electron's worth of charge down here, so 1.6 times 10 to the minus 19, and work out how many joules that's equivalent to. And that turns out to be relatively simple, so the work done is voltage times the charge, but the voltage is 1, so that's just going to be the charge with, instead of coulombs, it's going to be joules. So 1.6 times 10 to the minus 19 joules. So an incredibly small amount of energy. So why on earth would we want to deal with that? So that's the equation which we've just used. Oh, where's our diagram disappearing to? So this is the accurate value. It's known a bit more than 2 significant figures. And that's our definition there. So we define the electron volt in this way. So why on earth would we want to use an electron volt that isn't an SI unit and represents such an infinitesimally small amount of energy that surely it can't be useful to anybody? Well, let's think about the energy in photons, for example. So using Planck's equation, E equals hf, we know that h is in the region of 10 to the minus 34, and so is itself very small. And what this means is if we work out the energy of even a gamma ray, which has got a frequency of So the frequency of gamma rays is still something like 10 to the 19 hertz. But 19 minus 34 still means that we're talking about energies that are a billionth of a joule, and even the highest gamma rays ever discovered coming from an unknown location out of space are still looking at a millionth of a joule. So when we start talking about individual particles, it turns out that the electron volt becomes quite useful. So it's used, although it's not an SI unit, it's used quite commonly in atomic, nuclear, and particle physics. And we'll see the sort of scales. So if we're talking about the region of a tenth to 10 electron volts, so suddenly we've gone from talking about 10 to the minus 18 to 10 to the minus 20 joules, we're now talking about 0.1 to 10, so much more still numbers, not quite so ghastly to look at. And it turns out this is about the energy of a photon in the visible spectrum, so something in the region of red to blue light, maybe inching into the infrared and the ultraviolet. If you look at the single molecule, the energy of a single molecule at room temperature, it's got about this much energy. If you look at the bonds in a molecule, it's got about this much energy. If you look at the amount of energy required to strip an electron from an atom, it's about this much energy. And linking back to the photoelectric effect, the work function of metals, so the amount of electron required to remove an electron from a metal, is about this much. So it turns out that all of a sudden we've gone from something that's an infinitesimally small amount of energy represented by ugly, small, tiny numbers with 10 to the minus of huge numbers into something much more civil. We can just use this electron volt and everything becomes much nicer all of a sudden. And that's really all that there is to discuss this lesson. Is just this, the concept of the electron volt, the definition of it, what its value is. So as we saw earlier, the exact value is 1.6 times 10 to the minus 19, or 1.602176649 times 10 to the minus 19 joules is 1 electron volt. And this is used as a non-SI, but still, well, I guess kind of semi-standard unit of energy when we're talking about the particle world, looking at right on the very small fundamental particle level. So that's all for today.